So let's review what we just proved. What is Bézout's theorem? It essentially says you can write an equation of this form for some s and t integers. So now let's talk about how can we do this explicitly. So s and t in this expression are called Bézout coefficients. And we can compute them. So like I said, the Euclidean algorithm is going to tell us more than just the greatest common divisor. We can compute these guys as well, basically from the Euclidean algorithm. And we do that essentially by working backwards. So let's do a quick example of this. Forgive me for all of the computation, but just want to give you some examples to reference so that when you go and do lots and lots of practice on your own, you'll have something to look at if you get hung up. So for example, we saw that the GCD of 17 and 22 is 1. Let's use the Euclidean algorithm to verify this and then find Bézout coefficients. So 22 is equal to 17 plus 5. And then 17. I mean, this one you really probably can do in your head at pace is 3 times 5 plus 2. And then 5 is 2 times 2 plus 1. And so this thing is the greatest common divisor, right? If you wanted, you could write 2 equals 2 times 1. Okay, but then you're done. So how do we find Bézout coefficients? You start from this greatest common divisor, and you sort of work back up to express it in terms of these original numbers. So let me demonstrate how that works. So this is Euclidean algorithm, this is Bézout coefficients. So we can rewrite this equation as 1 equals 5 minus 2 times 2. Right? That's just rearranging this. And now we keep going where we keep the 1 on this side and we just rearrange and substitute the right-hand side to work our way back up the line. So if we rewrite this equation, we can express 2 in terms of 5s and 17s. And then we can substitute that in. So 5 minus 2 times, what is this? This is 17 minus 3 times 5. And this can be a little bit strange to understand because you have to keep track of which numbers you're treating as variables somehow, and which numbers you're treating as constants somehow. So you're keeping in mind that I want to preserve the 5s and the 17s in this equation. So I'm going to sort of solve for those, simplifying with that in mind somehow. So this is how many 5s are there? This is positive 6 plus 1. So that's 7 times 5 minus 2 times 17. Okay. And now I'm going to substitute this equation for the 5. And when I do that, I'll be down to 22s and 17s. So then I will have what I want. So 1, and I'm going to substitute in here. So 1 is equal to 7 times 22 minus 17, right? This equation is telling me that 5 equals 22 minus 17. So 7 times that minus 2 times 17. And again, we're keeping track of our 22s and 17s, and we're rearranging to bring those things out. So we get how many 22s? I believe we just have 7 of them. And then how many 17s? We have -7 minus 2. Okay, and that is the final expression that we were looking for, right? So let's just write it again more explicitly. 1 equals s times 22 plus t times 17. S is 7, and t is -9. So these are our Bézout coefficients. And it's worth mentioning that there are going to be more than one pair of Bézout coefficients. There are going to be many ways to write these things, but you will always find one using this technique.